some recent progress for this kind of line of research that I have been working on for a few years now. That is a new approach for attempting to reduce the computational cost of simulations of quantum matter using machine learning. So this is the outline of what I would like to talk about today. So in the first part, I would like to talk about the physics content. So motivating why it is important to simulate quantum matter on a computer. Quantitative methods we can use are available, and I would like to give an overview about that. And then I would like to say something about how machine learning can help us in this field, and finally summarize and conclude. Okay, so let's put a little bit of general context about what this is all about. So from a very broad perspective, what I'm going to talk about today concerns a key challenge in science and technology. By the way, the mouse is not showing up. That is the challenge of describing quantitatively the behavior of quantum matter. So properties such as specific heat, energy, magnetism, superconductivity, but not from a phenomenological perspective, but truly starting from the laws obeyed by the elementary constituents of matter in a quantitative fashion. And this is, of course, very important from the fundamental perspective, because it's about connecting physics at different scales from the microscopic to macroscopic. But it's also important in practice, because ultimately materials are useful for society and technological applications. So it is important to design materials with functional properties. And to put things a little bit in context, I want to also point out that we are living already now into a completely different paradigm from the original trial error approach when it comes to materials development with functional properties, where theory and simulations is playing an important role, increasingly important role. And in fact, it's not even that uncommon nowadays that materials are first theorized and characterized computationally, and only afterwards also synthesized and characterized experimentally. So this is to give some context. And what kind of methods are typically used? So first of all, to give a sense of the scale, this is not something that is only going on in solid-state physics, condensed matter, but also in chemistry, material science, biochemistry, nanotechnology, even drug design is often approached also using this sort of first principle calculations are called. So really doing simulations on a computer. And there is a key method amongst the many that exist and that I have here in this cartoon represented symbolically, that stands out in terms of how much is used in practice throughout all of these different fields, and that is called density functional theory. And here, of course, I don't want to go into details at all about how this works, but I just want to point out two things. So why does it stand out is that, pretty much you can imagine that all of these different methods available have different level of accuracy and computational cost. That is supposed to be on the x-axis here, but it's covered by the Zoom link. But density functional theory compared to other methods with the same kind of cost has a higher accuracy. So this is why it stands out so much. And then another thing I want to point out about this method is that it is based on a physical picture that is approximate, but can be also rigorously justified in certain cases. And that is the picture of describing the electronic structure in quantum matter in terms of something called block waves. So electronic waves that they propagate kind of independently from each other throughout a periodic system or a molecule. And this is something highly non-intuitive, and in fact, the foundation of this approach of this model is based on the so-called Pauli principle that is obeyed by fermionic particles such as electrons. But this is kind of like the key model that is used in all of these fields of applications. But the point is that this doesn't always work. It works only in certain cases, but doesn't work in the so-called strongly correlated materials. And to first approximation here, I want to refer to systems involving a d or f electrons in the external shell. That is the kind of electronic, the shell that governs the chemical and physical behavior of matter. And so we can think about systems involving transition metals that are in this box, or lanthanides in this other box, or actinides in this other box. And the key thing that is going on when we have systems involving these atoms is that we are often in a situation such as this one in the bottom, where the electrons that are these blue clouds here are more localized around their atomic positions, as opposed to this kind of picture where they kind of overlap. And what's going on is that because of this reason, all of these kind of atomic energy skills that we can learn when we study chemistry in introductory courses, such as multiplets and Hund's rules and things like this, emerge explicitly in the observables also for extended quantum systems. And so we need to capture these atomic energy scales, and simply they are not present in this scenario that I was outlining before about electronic waves propagating independently. So they simply don't appear explicitly. And so that's the reason why this approach is often fails. And this is something that we would like to avoid. Now I want also specify two things for a minute. One is how we kind of model the systems. And I will not go into math, of course. But I want to give still a physical sense of how things go. And also I want to give an example about what I mean when I say that these atomic energy scales emerge explicitly in the observables. And for this purpose of exposition, I would like to think about, have you introduced this Hubbard model that is a very important model in solid-state physics. And what this model represents is that you may have a lattice, such as this one, where each of these red dots represent like a site, a position in which electrons can go. And this first term of this Hamiltonian, the Hamiltonian is a mathematical object that we use for describing the behavior of quantum systems, encodes the fact that electrons can hop from one of these sites to another. So these sites are represented by a label, I and j, some integer, and they can hop from a site to another. Electrons can move throughout a material. But then we have this other second term proportional to this constant that is meant to be positive, and it's called Hubbard repulsion, and is U here. And this is accounting for the so-called Coulomb repulsion. So the fact that, as you know from electromagnetism, electrons, since they have the same charge, they repel each other. And what this means is that they don't like to stay in the same site simultaneously, because they like to repel each other. And so this is essentially putting some sort of energy cost to configurations such as this one. And there is an interplay between these two different terms that is different and creates differences between metals and insulators and other features that we may have in different materials. It's all encoded in these sort of parameters in this model. So what would happen? Of course, this is a simplified model. Real materials are more complicated, but it captures a lot of the physics going on here. And if you would perform spectroscopy measurements on a system represented by this Hamiltonian, this is what would happen. So first of all, what is photoemission spectroscopy? So I refer to the photoelectric effect, the fact that if we shoot light on a system with a certain energy, there will be an electron that can be eventually kicked out. And we can detect experimentally the energy of these electrons as well as its direction, where it goes. And that informs us about the available excitations that the system can have that are not free. They depend on the specific model we have. And certain energies can be available to be excited and others not. And so this is what we would kind of measure if we would perform such a measurement on this kind of system. We would have something completely different depending on this value of this parameter U. Here, I don't mean to go into details. I just want to mention that having some sort of signal here at 0, the so-called Fermi level, this means that the system would be a metal, and here would be that the system is an insulator. And this scale U that we can refer to as some sort of atomic energy scales because it's local. It belongs to the single site I. is just the distance between this different excitation. So it explicitly emerged in the observables, as I was kind of saying before. All right, so this explains why we want these atomic energy scales and why we don't want to rely only on these block wave scenarios. And now I want to also show something about what does it mean in practice when you want to make simulations and you want to be accurate, okay? So I like to show, for explain this point, some results from this paper of a few years ago, where we looked at a series of binary compounds with just 2 atoms, where the first one is a transition metal. So it has some open D shell, and therefore we have this expectation that we may have this sort of importance of these atomic energy scales that we refer to as strong correlations. And this is a plot that represents simultaneously different features that these different materials can have at standard ambient condition of pressure and temperatures. So what we see is that we have some symbols that they have colors. Colors represent the kind of structure that they have. So these are lattices, so there is some sort of unit cell that is repeated periodically. That's the kind of structure they have. And all these structures have different names. And having a blue here means that we have a structure called an IAS, and having green here means that we have some structure called rock salt, and we can have different structures. So the color dictates this. These are all for now just experiments, so circles that means experiments. And whether the symbol is fully colored or half colored and half white, like this, dictates whether this is a metal or an insulator. So we have all these different features. And on the y-axis, we have the volume of this unit cell that dictates how much mass density there is. And they have all different density and different properties. Now, if you would rely on a typical approximation that is based on this idea of electron waves propagating independently, we would get some disagreement. Okay, so theory that are these triangles and the experiments wouldn't match pretty much for any of the properties. But when we do take into account these atomic energy scales with methods that I'm going to outline in a second, then we recover this accuracy that is satisfactory for all features simultaneously. So this is to give some context about why it's important to perform such simulation. But the key point is that we still don't do it because all of this type of method that can tackle this correlation effects kind of stay here in this area. The computational cost is prohibitively high for many interesting applications. So right now, we still need to use density functional theory. But then here comes the question, how can we incorporate this? And I want to already start to outline what is the idea here about machine learning. So the scope that we are talking about here is that maybe machine learning can speed up, reduce the computational cost of this kind of calculation and bring them here on the diagram. That would have a huge impact. So that's the goal from a broad perspective. That's what we want to achieve. And gradually, we're going to get into explaining how I think machine learning can help and show also some benchmarks. Okay, so this leads to the point of how do we take into account these local atomic energy scales in methods. So before to get to the machine learning part, what is the kind of calculations that we need to do so that we can later say where machine learning could play a role. And the idea is as follows. These systems are generally so big, these lattices are extended. There is no way to solve this electronic structure problem exactly. This is impossible. So there is a common idea to many, many methods that is used, and that's the whole idea of a quantum embedding. The idea is actually fairly simple. The idea is that you have an extended system, but you can consider it as composed by fragments, these red dots, interacting with each other. They interact with each other. And so what these methods are doing, starting from different principles often, is to try to describe the interaction of each fragment with its environment in the system of interest using an auxiliary system that is simpler to solve. This can be called embedding Hamiltonian or impurity model and consists of one of these fragments and some other degrees of freedom that are auxiliary. They don't really exist in the real world, are auxiliary, and are meant to approximate as well as possible the interaction between the fragment and its environment in the actual system of interest. So that's the goal, that's the idea. Of course, all the details here go in how do you even construct that, but from the point of view of a big picture algorithmic structure, this boils down into some sort of iterative procedure where at each iterations, the parameters that characterize this auxiliary system that we just call X, you can imagine it's a big vector, some big array, characterize one of the system. We need to make a computationally expensive things that we can do and evaluate some observable out of that. So ultimately, mathematically, what we're doing is very common. Also in other areas, we are just trying to evaluate the function, but that's an expensive operation. That's the expensive operation that is the reason why these methods are more expensive than others and where the limitation stands. That's the computational bottleneck. The interesting fact, number one, is that since we are going to solve this exactly, all of these atomic local energy scales are actually captured exactly. So that's why this kind of works. From the computational perspective, the interesting thing is that this function that we may want to evaluate that depends on the specific system, and we're going to specialize to one, is universal in the sense that it does not depend on the material you study. So in other words, we are dealing with some sort of regression problem. If we could learn once and for all from data this function, we could simply bypass the problem of computing at each iteration this complicated problem. So that's kind of what we want to do. Have a machine that learns these functions once and for all. And if you could do that, then we would go here in this diagram. And this problem would be completely changed and reduced. Now, of course, this is not simple. I will need to explain why. Before to do that, I want to say that we are not going to use a generic quantum embedding methods, but a specific one called Gauss-Willer approximation that I developed a few years ago, and now it starts to become kind of used by a lot of groups. And the advantage from our perspective here is that the function that we have to learn is a scalar function. We don't have to learn a vector function, just one scalar function of some big vector X. That's the setting. Mathematically speaking, that's the setting. We need actually to learn it along with its gradient, which we call f. So that's the problem. We have some machine that has to learn a scalar function along with its gradient, and we want to get from here to here. All right, so now how can we do that? So here comes the machine learning side of the story. And I want to start from an analogy to something that you know better than me. That is the image recognition problem, which is kind of present similar difficulties. The similarity is that also in that case, we have a huge ambient space, a huge dimensionality of all possible image, all possible combination of pixels. And image recognition means that essentially you want to assign to an image a combination of pixels, some sort of output, which is ultimately a function. It may be a discrete function because you just want to know if it's a giraffe or something else, but it's still a function. The key point in common here is that you have a high dimensionality array as an input. But the point also that makes it possible is that we have some prior knowledge, things that we see as we navigate the world look like nothing like salt and pepper image, random combination of pixels. They have correlation length. They have things that exist in the world very simply, and that we need to navigate, and things that we simply, majority of combination of pixels that we don't care. And my understanding is that this is referred as a latent space of image that is of much lower dimensionality with respect to ambient space. And if this wasn't the case, this would be a hopeless problem because of the so-called curse of dimensionality. So what's the analogy here is that here, instead of having all possible image, we have all possible parameters of this embedding Hamiltonian that physically represents all possible interactions that a fragment can have with its environment in a molecule or in a solid. And these are also not random mathematical arrays. Like, they are going to be constrained by physics. They're going to be constrained because there is structural stability. You cannot put a molecule in whatever configurations you want. There will be a stable structure, and the other structure will be unstable. There are things such as valence compatibility. There are all sorts of constraints. So there are good reasons to think that maybe the set of physically relevant parameters in this large dimensionality space of mathematically conceivable embeddings, so these parameters X, actually we only need to learn this function in a very low dimensional manifold. a lattice space with smaller dimension. So that's kind of where the analogy stands. But there is a key problem that is how can we even exploit this low dimensional structure, even if it exists in practice? Because the point is that we don't know it a priori. We don't know a priori what kind of physical embeddings we may encounter, what kind of physical environments a fragment may find itself into as you navigate the set of all possible materials and molecules. So in some case, in the previous work, we were able to kind of conjecture based on domain expertise where this latent space is. But in general, this is not possible. How can we tackle this in general is the subject of this work that I want to kind of now show something about, that is going to be hopefully online in a couple of weeks. And this is the idea that we wanted to use, that is not uncommon in other contexts, but it's the idea of using an active learning approach. So the idea is that we don't want to pre-train in advance this machine. What we're going to do instead is different. As we go through this self-consistency procedure that we have to do anyway, and some parameters X are given by this sort of loop, we don't directly make a calculation. We try to fit it into a machine. And this machine may have an empty database of previously acquired data about this function, or may have already some data. And depending on this data, we want to have some sort of uncertainty quantification, some level of confidence that the machine may have into what the function does at that particular point X. And if this level of confidence is above a certain threshold, new data are acquired because we don't have enough accuracy. And so when new data are acquired, the machine now is informed of this new data and the new estimate is made. Otherwise, the machine directly makes a calculation and bypasses this computation. Now, by construction, we are only navigating physical embeddings because these are calculations that are made while studying physical systems. So we don't need to go through exploring the whole ambient space of possible X's, only those that are relevant for us by construction. And what we would like to is to have this metric to be as small as possible. So if we go to iterations, the number of data that we want to acquire has to be as small as possible with respect to the total number of iterations. Does it make sense? Yeah, this is kind of the setting that we want to implement. And we want for that purpose some sort of uncertainty quantification. And this can be done in many ways. Also with neural networks, there are ways to do that. Here we did it using Gaussian process regression, which you probably know way better than me, but let me outline it from my perspective. So the idea is that we have some function we want to learn, and what we want to construct when we make our prediction is a conditional probability. So given a set of data, what is the probability that we have for a certain energy function? This will have an expectation value that is our prediction, but also an uncertainty that is the variance of this probability distribution at each point. And this is something that we can construct using Bayes' rule from some prior knowledge, that is the prior and the data. There are two terms that are multiplied. And the prior knowledge is encoded in something that in physics we would call a correlation function. And in machine learning is called a kernel function, but it's the same thing. And this is something that essentially encodes what you expect the function to look like at the big scale in terms of some global features. So in particular, if we use this thing called square exponential function, this L parameter would be like a correlation length. So how smooth the function is, how rapidly does it vary. We don't expect, if you use something like this, this function to vary very much for scales much smaller than L. That's what it kind of means. And this prefactor instead is kind of giving us information about the magnitude that this function may have. So do we expect it to be very large or very small? That's encoded in this parameter. So we can gather this information and combine it with data. Data can, in some cases, be probabilistic, like in example, if we would use a quantum device to compute the data, to evaluate this function, they would be non-deterministic inherently. But in our case, they will be deterministic. So essentially, there will be no uncertainty over the data. And so this conditional probability will be pinned at the data. And this is essentially what you will have. Let me see if it works. Yeah, you will see a situation like this where we want to learn a certain function. The more data we acquire, the more we can characterize this. Oh, now it works. accurately. We also have this uncertainty quantification. And as we move away from the data points available, the uncertainty gets bigger, as you may expect, right? Perfect. So this is the kind of situation. Now, what we use is actually something that is a little bit more complicated. It's a variant to standard Gaussian process where we also account for gradient information. So we not only learn the function using data of the function itself, but also gradients. And so, for example, if you would like to learn this yellow function here, without the gradient, we would get this sort of result. But if instead we also provide to the machine information about the gradients at this point, with just the same number of points, we get way higher accuracy and more faithful description. So we use this variant here. This comes with some extra computational cost, and there will be details that there's no time to discuss now, but maybe in the discussion session I can get into that has to be tackled, but this is in principle possible. And so now, does it work? So what we need to do to see if it works, we take a series of models. We take a models like this. In this case, that is kind of like an experimental setting where we are testing things for the first time. The ambient space, as just mentioned, just 6. It's not that big of a dimension, but enough that if you would have to explore the whole ambient space, it would be unfeasible. 6 is not that small already, if you want to do things very naively. And what we want is, again, to minimize this metric of how many new data we need to acquire along the way. We want this to be as small as possible. And we test this on this model, not only on the sort of structure that we checked before, but also on different structures. This is a square lattice, this is a cubic lattice. And we want to do this sort of calculations for this type of situations. And there are 3 things we wanted to check. And let me explain what we did here. So we are monitoring now, while performing a calculation such as this one, this metric. And on the upper side, on the horizontally, we're basically taking sweeps of these parameters U, fixing the structure. So this matrix T is fixed. We're taking sweeps of U, and please focus only on the upper side of these different panels that have colors. This is if we start from an empty database for a given delta U is the mesh spacing of the parameters U that we have. And we see that even if we start from an empty database, we do save something. We do save something, and the reason for that is that this is not these axes that we explore don't move randomly. They converge towards the point. So as we approach that point, we are learning the energy landscape around that point. So this turns out to be sufficient to get some saving, even if you start from an empty database. And this white in the bottom just means that if you would try to repeat those same calculations, once we acquire those data before, the machine would just not require any more iterations. This is, I'm referring to this as monotonic learning in the sense that as you acquire new data, you need less, you have sufficient stability in the algorithm that in the end, you truly can exploit this data for future prediction. And in this first plot, just to identify the specific stability feature, every row corresponds to a new resetted database. So we remove the previously acquired data. We don't have any new data as we check a new mesh. Now, in this other plot, what we did is different. We have 2 different models of data acquisition. So in the top row, we reset the database every time. So we always start from an empty database. And instead, when we look at the lower set of colors, we are measuring this metric, but we keep acquiring new data and we don't throw them away. So and what we see is that this is closer to the white. So we have more savings. So we can take calculations for certain parameters and use them to make predictions about the model at different parameters. That's what it means. So we still need some calculations to be performed along the way, but not all of them. And especially for large parameters U, where we have this strong correlation regime that I was talking about before, the savings, this metric is particularly small. You can see the savings are being very high. So this is something that needs to be explained, and I will get to that in a minute. Now here we also change the structure and we see similar patterns. So if we start from an empty database, we do see some savings. If we exploit data previously acquired from different structure, different kind of geometric configurations, we can use information gathered while performing calculations of different systems, looking completely different. This is two-dimensional, this is three-dimensional. They are completely different. We can use that information and continuously make this machine more efficient as we acquire new data. So that's kind of interesting and important also to point out. We seem to lose zero accuracy. So the dots here, blue or orange, they correspond to data acquired, calculation performed using this active learning procedure, where the machine is used and saves computational cost. And the continuous line corresponds to data where we just perform the calculation brute force at each iteration. So we lose no accuracy in all of these calculations, but we do save some computational cost. And in principle, if you have a very large data set, this could become even more efficient. At least that's the goal, right? Now, why this trend? So what we did is the principal component analysis of the whole data set at the end of all the calculations I have shown. And we marked in colors the calculations that correspond to final points obtained after convergence. So we have an iterative procedure here. This exchange for each point, change, until it stops because it reached the final value. So this final value is colored in red, blue, or green, depending on the structures where we are. This blue corresponds to the Bethel lattice. This red corresponds to the 2D square, and this corresponds to the cubic. So this, and the gray corresponds to the data acquired throughout the self-consistency procedure. Those that are not the final point, and they gravitate around the final point because of the nature of the calculation that has this aim of converging towards a certain point. And so what we see is that, first of all, two principal components are enough for capturing most of the data set, which is already interesting because the ambient space had dimension 6, but there are only two principal components, means that all of this data kind of almost lie on a plane, on a two-dimensional subspace. But not only that, there is some sort of underlying almost one-dimensional structure, which means it's something we could leverage on with machine learning. So this idea of physics constraining this latent space of physically relevant embedding sounds promising in this sort of calculations. And interestingly, in this strongly correlated regime, there is almost overlap between different geometric structures. And this is also very intuitive, because if you are in a situation kind of like this, it means that the fragments are closer to be isolated, and which would suggest that the details of their environment, of their geometry, become less important than when they interact very strongly with their environment. So this is also why we saw a lot of extra gain computationally in this regime compared to this regime. Yeah. So in summary, what we did is to introduce quantum embedding simulations and their role, what we aim to achieve essentially, there is some idea of a latent space of physically relevant embedding that can be leveraged on with machine learning, and we propose an active learning approach to do that. That doesn't assume prior knowledge about where this latent space lies from the beginning. So, and the goal was to remove, and still to remove the computational bottleneck of these quantum embedding methods for extending the range of applicability by reducing dramatically their computational cost. And with this, thank you for your attention. Was I on time? Maybe too late? That's great. Okay.
Questions?
I'd be happy to take questions. I guess it's an uncommon kind of topic in this room, right? But yeah, machine learning is everywhere now. So